A pop operation in the stack refers to removing an element from the stack. And as we know that the stack follows the LIFO principle, that means the last element that was inserted in the stack will be the first one that will be taken out. So let's see how a pop function can be defined. So we have the main function over here, and from the main function I should be able to call a push operation or a pop operation. So let us see how the pop function will work. Also, since the stack has to be accessible in all the functions, we declare it as a global variable. So we have an array. Since we are implementing the stack with an array, we have an array of size n. We have defined n to be of size 10, but we can declare it straight away like this also. We have another variable top, which was initially initialized to a value of -1. -1 refers to a empty stack. However, we see over here in the current status of a stack, we already have an element 2 and another element 7. So considering that the indices of the array are starting from 0, that means the variable top is at value 1, since the topmost element of the stack is at index 1. If we do a pop operation, one element which is at the topmost side of the stack would be removed. Since 7 is at the top of the stack, 7 will be removed and top will be decremented. So top will now point to 0. When we are popping out, it does not necessarily mean that the element has been deleted. It is over there, but it is a garbage value now and it is not part of the active stack. The active stack is only this part of it is the active stack. Like earlier, the active stack was only this. On deleting or popping out the first element from the stack, the active stack is only this much. So even though 7 might be present over there, and it will be till the time it is overwritten, but it is not part of the stack anymore. If we do another pop operation, then 2 will also be removed from the active stack and top will be decremented. So top will now be -1. And as we said that this represents an empty stack. If we do a push operation now, so if we say a push 5, that means top would be incremented by 1 because this is the currently next available free space. So top will be incremented to point to this new space and 5 will be inserted over there. So top would have a value of 0. So every time pop operation takes place, top is decremented, and every time a push operation will take place, the top variable will be incremented. So here is that function pop, and it simply says top minus minus. That means simply decrement the top. That is all that needs to be done for a pop operation. However, before deleting an element from the stack, we should always check whether the stack is empty or not. If the stack is empty, that means there is no element that can be deleted, and this is an underflow condition. So when would the stack be empty? When top is -1. So if top is equal to -1, print that there is an error and there is a chance of a stack underflow. Else, if top is not -1, that means we are still having elements in the stack. So simply decrement the top. There is no need to remove elements or change these values to anything else. What will be the changes required if the popped value is to be printed? So here, before decrementing the top, we'll print the value which was available at stop. We will do this printing and then decrement the top. So if top was currently at this position and we print s top, then 2 would be printed out. So this is 2 is the value that is being popped out, and then we can decrement the top to be -1. So what is the complexity of the pop operation? Since just one element which is at the top of the stack is popped out, the time complexity is order of 1.